Okay, calculating the voltage of a galvanic cell. I'm just going to do a couple really quick examples here where we're going to see how to do it if you're actually given the galvanic cell in this notation. So here we have iron that's going to go to iron 2 plus, and copper 2 plus is going to go to copper. This is representing our anode. This is our cathode. And we're going to see here. So we're looking for iron and zinc on this. Iron 2 plus specifically, so we're looking here, and copper 2 plus specifically, so we're looking here. So we're comparing this reduction right here to this this oxidation. So the oxidation Fe is going to Fe2 plus 2 electrons. It doesn't matter how many electrons because this number is given as an amount of energy per unit charge, so we're not even worrying about that. So negative 0.44 volts, but because we went backwards, we would switch that to being positive 0.44 volts. Right, we have to reverse that number. And here, copper, this is in the proper direction, going to form elemental copper, and with a voltage of 0.34 volts. And we keep that one as a positive because it's in the same direction as it was. These two electrons happen to match up with each other, but don't get fooled by that. If they didn't, we wouldn't do anything differently. So we get 0.44 volts from the reduction of the iron, and 0.3 volts from the oxidation of the iron, and 0.34 volts from the reduction of the copper. And so our voltage here is going to be 0.78, the total of those two things. Now, I don't want you to get confused if you see an example like this, where we have an inert electrode. An inert electrode simply acts as a location, maybe a catalyst, to allow the electron exchange between two things in the solution that are both participating in the actual reduction or oxidation, depending on what's going on in that. So here, platinum is inert. It's not actually getting used up. It's not actually participating in the reaction, but instead, it's just the location where the electrons are going to go or come from when H plus is reduced to H. So at our anode, we have zinc being oxidized into zinc 2 plus, producing 2 electrons. And we look here, and zinc is right here. So it's this process, but it's happening backwards. So instead of having negative 0.76, we're going to have positive 0.76 volts from that. And here is the secondary process. We have hydrogen being reduced into hydrogen gas, and that's our standard. So I'll show it to you here, on the chart, but you don't need to look it up. That's our standard zero reference point. So that's going to have a voltage of 0 regardless of which way it's happening. And again, we happen to have 2 electrons and 2 electrons, but we're not even paying attention to the number of electrons when we're predicting these voltages. These voltages are per unit charge. So my total voltage here is 0.76 volts, 0.76 plus 0. So we write out the oxidation and the reduction. Since the oxidation is going in the opposite direction of this chart is written for reductions. We take the sign on whatever voltage is associated with that and we flip it, and then we can simply take the sum of those two things without accounting for the number of electrons. Also keep in mind that it might not make any sense, for example, to have energy produced when an atom loses its electron, but do remember that all of these energies are being measured not to an absolute zero energy point, but always relative to the amount of energy associated with the reduction of hydrogen, so we can get some negatives and positives in places that don't make sense, other than when we consider them relative to the amount of energy associated with that reduction of hydrogen.